In this video, we're going to talk about some notation for derivatives, and I'm going to show you, I'm going to show you a bunch of examples of some common functions that we take the derivative of, and try to convince you of the first rule that we're going to talk about, the power rule. Okay, so this is one that is used a lot. The textbook does prove it a little bit more generally. If you're interested in that, I'm just going to try to convince you of why it might be true, or convince you to see the pattern at least. So for some notation, okay, so suppose that we have a function y equals f of x, and we want to talk about its derivative. Okay, so what we were using before, f prime of x, okay, or okay, you might say y prime. So this is f prime of x, and here we have y prime, or you could say y prime of x if you include the x there. Some other notations that you might see, dy by dx. So what this says is it's the derivative, okay, of y with respect to x. So what that means is x is your variable. Okay, you might also see df dx. Okay, so similar to dy because our function name is f. Or you might see d by dx of a function f of x. So this one is slightly different because it's saying it's the derivative, okay, with respect to x of the function f of x. So this particular notation here can be useful if you want to show your work. So you might want to show that you can do this. You might want to take some derivatives and not others. And this is a way to show you and your reader that you haven't yet taken the derivative of this function, okay, but you intend to. There's another one that we're not going to see very often, but also exists, d sub x of f of x. Okay, is another one. So again, here this x is your variable. So you might wonder why we need this of d of x. Why do we need to indicate what our variable is? And the reason is, in this class, we usually will just be working in one variable, but it's possible that if you go higher in math, or in some specific cases here, that we might have more variables going on. So it's very useful to be able to talk about which variable you're working with. And here they do that by saying of x in the prime notations. Okay, so you might have y prime of x to indicate the variable. Why do we have these two notations? Well, calculus was independently sort of developed by Sir Isaac Newton and Wilhelm von Leibniz, and they use different notation. Okay, so that's why we have this different notation, and they each have their own advantages and disadvantages. Okay, so in certain scenarios, we're more likely to use one over the other. So they're sort of all in use throughout calculus today. So just to give an example of how we use this, we in the last video took the derivative of x squared plus 3x. So we saw that f prime of x was 2x plus 3. Okay, so we might also write df dx, okay, equals 2x plus 3. Or we might write d by dx of the function x squared plus 3x, okay, equals 2x plus 3. Okay, so those are all different ways to write the exact same thing. I don't like those 2's. So that's how they're used. The same notation holds when the variable changes. Okay, so we don't have to use x all the time. We might have y as a function of t, for instance. We often talk about over time, so sometimes we use variable t. We might change the function name. So here our function is called capital P. But the notations are the same. Okay, so here we could have y prime of t, or p prime of t, or you could have dp dt, or you could have dy dt, or you could have d by dt of p of t, okay, etc. So notice that t is our variable, so that's why it's in the bottom of all of these d by things, and inside the brackets in these other ones. Okay, so it doesn't matter, the notation just corresponds to your function name and the variable name. Okay, so now to some basic derivatives that we use frequently, and I'm going to do all of them with the limit definition, so that that's the only way we know how to do things right now. So the first one I want to talk about is the derivative of a function that just is a constant. Okay, so there's no x's here. So if I wanted to use the limit definition, f prime of x is the limit as h goes to 0, f of x plus h minus f of x all over h. Okay, so now for my function here, that's just k, when I take f of x plus h, normally everywhere I see x, I put in x plus h. But our function has no x's. So this is just k. So f of x plus h is k, and so is f of x is also k. Okay, so what we end up getting is the limit as h goes to 0 of 0 over h. So here I just want to point out, the top is exactly 0. Okay, so it's not approaching 0, it is 0. Whereas the bottom is approaching 0. So this is a bit different than our 0 over 0 case, because the top isn't approaching 0, it is 0. Okay, it doesn't depend on what h is doing. Okay, it just is 0. So this is actually the limit as h goes to 0 of just 0. Okay, and when we take the limit of a constant, it's just a constant. So when f is a constant, this is our constant rule. When our function is just a constant, the derivative is always 0. Okay, now another way to see that is with a picture. So if I have a function y equals k, it's a horizontal line, right? So when we take, if we take a derivative at a specific point, when you're on a line, the tangent line is the line. Okay, so this would be the tangent line. This line has slope of 0 for all values of a. So that means that the derivative is the slope of the tangent, so it should be 0, no matter what the a value is. So whenever you're taking the derivative of a constant, you should get 0. Okay, let's try another one. What if my function is just x? Okay, so f prime of x is the limit as h goes to 0, f of x plus h minus f of x all over h. So again, everywhere I see x, I put in x plus h. So f of x plus h is x plus h, and f of x is just x. So I have x minus x, those go away. So this is the limit as h goes to 0 of h over h, which is the limit as h goes to 0 of the number 1. And again, when we take the limit of a constant, it's just the constant. So here we have the derivative of x, okay, is just 1. And again, I can show you this one with a picture, without too much effort. Okay, so why does it not depend on x? You might be wondering. So the graph of this function is the line y equals x, which looks like this. So again, at any a value, okay, the tangent line is the line. Is this line, which is not horizontal. This line at every point has a slope of 1. Okay, so that means that our derivative at any point a has to be equal to 1. Okay, it doesn't depend on x because the slope is the same no matter what x value you plug in. So if we take the derivative of an x, we just get a 1. Okay, what about an x squared? So I'm going to skip the f of x plus h minus f of x all over h and just plug in. So f of x plus h, I plug in x plus h everywhere I see an x. So I get f x plus h all squared minus x squared all over h. If I expand this out, I get x squared plus 2xh plus h squared minus x squared all over h. X squared minus x squared, those go away. Okay, so now I see every term on the top here has an h in it. So I can factor out the h, and I'm left with 2x plus h left over h. Now I can cancel those h's. So it's the limit as h goes to 0 of 2x plus h. And now I can evaluate the limit. So this is 2x plus 0 or just 2x. So the derivative of x squared is 2x. Okay, one more of this type. So what about x cubed? So f prime of x is going to be x plus h all cubed minus x cubed all, oh, I missed the limit. Ooh, I should never do that. Let me just put the limit in there. It's the limit as h goes to 0 of what I just wrote. So x plus h cubed minus x cubed all over h. Okay, so now we'd have to FOIL this all out. So it's x plus h times x plus h times x plus h. I'm just going to write what it expands to, but you should make sure that you can expand it to this. So it's x cubed plus 3x squared times h plus 3x times h squared plus h cubed. Okay, I see I have an x cubed and a minus x cubed. Those go away. And again, all my remaining terms have an h in it. So I'm going to factor out that h. So I'm left with 3x squared plus 3xh plus h squared all over h. Okay, these h's cancel out. So I have the limit as h goes to 0, 3x squared plus 3xh plus h squared. And now I'm able to plug in h equals 0. Oops, I don't need the limit anymore because I'm evaluating the limit. So it's 3x squared plus 3x times 0 plus 0 squared. So I just get 3x squared. So the derivative of x cubed is 3x squared. So you might be seeing a pattern already. I'm not sure. I'm going to try a couple more different ones that seem a bit different, but actually are similar to the ones we just did. So what about the function 1 over x? Okay, so f prime of x is going to be the limit as h goes to 0, 1 over x plus h minus 1 over x all over h. So I want a common denominator on the top, so I'm going to multiply this first term by x over x, and the second term by x plus h over x plus h. So then this is going to be x minus x plus h all over x times x plus h. And then that's all over h, which we could think of as over 1. So I have a fraction over a fraction. So I'm going to flip the bottom one and multiply. But I'm also going to simplify the top as well here. So I have x minus x. So those go away. The minus has to go through though. So I get minus h over x plus h. And that's times 1 over h. So I flipped the bottom one and then multiplied instead of divided. Now I can cancel these h's because they're multiplying and everything, and one's on the top and one's on the bottom. So I get the limit as h, not x, as h goes to 0 of negative 1 over x times x plus h. I can now evaluate the limit. So it's negative 1 over x times x plus 0. And this is actually negative 1 over x squared. So it's x times x. So we get the derivative of 1 over x is negative 1 over x squared. Okay, one more. Square root. So here, f prime of x is the limit as h goes to 0, square root of x plus h minus square root of x all over h. Now I'm going to times by the conjugate. So remember, that's the same two square roots, but with an addition in between instead of a subtraction. Okay, so the opposite sign. So when I do that, I'm not going to expand the bottom. Okay, so it's just going to be h times the square root of x plus h plus the square root of x. The reason why I don't want to expand the bottom is that I'm hoping to cancel this h. So I want it to be multiplied into everything. Now on the top, when I FOIL this out, it's actually like a difference of squares. So what I'm going to get is the square root of x plus h all squared minus the square root of x all squared. So when you simplify that, the square root and the square go away. So I get x plus h minus x over h times square root of x plus h plus square root of x. And now these x's go away. And I have h over h times square root of x plus h plus square root of x. And now I can cancel these h's. I'm running out of room, so I'm going to move up here. So this is the limit as h goes to 0 of 1 over square root of x plus h plus square root of x. So now I can evaluate the limit. So this is square root x plus 0 plus square root x, which is square root of x plus square root of x. So it's actually 1 over 2 root x on the bottom. Okay, so the derivative of square root x is 1 over 2 root x. So now I want to try and get us to see a pattern here. So how are these all the same, and how are they all following the same pattern? So let's try and write them all out. So when I had k, so just a number, okay, this is times x to the 0, okay, and I got derivative, so I'm going to actually, let's do a table here. So we have a function, okay, and a derivative. So the first one we did was k times, and it's just k, so we could think of that as times x to the 0. So that's it, the derivative was 0. Okay, now you could think about this as 0 times k, okay, x to the, I'm going to write it -1 here, but that seems weird. But let's keep going. So my next function was 1 times x, so it's x to the power 1, and we got derivative just 1. So you could write this as 1 times x to the 0. Okay, when we had x squared, I guess I didn't need this 1 here. When we had x squared, we got the derivative 2 times x to the 1. Okay, when we had x cubed, we got 3x squared. Okay, now when we had 1 over x, which you could think about as x to the -1, we got 1 over x, -1 over x squared, which you could think of as -1 x to the -2. And our last one was root x, which is x to the 1/2. Okay, and we got 1 over 2 root x, which is the same as 1 over 2 times 1 over root x, which is 1 over 2 times x to the -1/2. So now notice, okay, this one is just 0, the top one. So it's maybe the least obvious. So I had exponent 1. The 1 came down, and then I got exponent 0. When I had exponent 2, the 2 came down, and I got exponent 1. When I had exponent 3, the 3 came down, I got exponent 2. Okay, now 1 over x is also a power of x. Okay, so the -1 came down, and I got -2 as an exponent. The square root was also a power of x, so it's x to the 1/2. The 1/2 came down, and I got -1/2. So notice that these new powers are always 1 less than what the power was. Okay, this is the idea behind the power rule, and I'm hoping this is enough to convince you. So if you have a function where you have a power of x, so a power of your variable, where n is any real number. So we only did it for integers and then one fraction, but n could actually be any real number. Then when you take the derivative, it's going to be n x to the n minus 1. Okay, so the other way to write this, d by dx of x to the n is n times x to the power 1 less than what it was, so n minus 1. So let's use this rule to compute some derivatives. So first of all, our function f of x equals negative 10. Okay, negative 10 is a constant. So what that means that we can use the constant rule and immediately say that the derivative here is 0. Okay, the variable is x, okay, and there's no x's here. That's just a constant. For part B, the variable is z. Do we see any z's here? No, we don't. And in fact, pi is just a number. So pi to the 7 is also just a number. So it's a constant. So that means that, again, the derivative, so g prime of z, okay, is 0. So pi is just 3.1415926, etc., etc. Okay, it's a number. So when you raise it to the power 7, it's also just a number. Okay, so those both have derivative 0 by the constant rule. Now in part C, our variable is t, and we have t's in our equation, but it's a power of t. Okay, so that means that we can use the power rule to say that the derivative is 15t to the 15 minus 1. So that's going to be 15t to the 14. Okay, that's our derivative for all t. Part D doesn't look like a power of r, so r is our variable here. That's the thing inside the brackets. But we can rewrite it, so this is r to the minus 2. So if we rewrite it, now I can compute the derivative using the power rule. So negative 2 r to the negative 2 minus 1. So that's negative 2 r to the negative 3, which I'd want to rewrite as negative 2 over r cubed. So we don't like leaving negative exponents usually. Okay, one more. Again, doesn't really look like a power of x. You might think we don't know how to compute this, but remember that the exponent rules tell us that this is actually x to the power 2/3 because we have a cube root of a square. So that is a power of x. So f prime of x, bring the power down, so 2/3 times x to the old power minus 1. So this is going to be 2/3 x to the negative 1/3, which you could think, so negative 1/3 is 1 over x to the positive 1/3. And when we're multiplying fractions, you multiply straight across, so it's 2 times 3x to the 1/3, which maybe you want to write as a cube root of x, if you like the roots better. Okay, that's the derivative there. So that's hopefully convinced you of the power rule and how we might use it.